So electric potential you can think of as kind of a height. The bigger the potential, the higher the charge is. You don't want to confuse that with electric potential energy. They're related, but they're not the same thing. Electric potential energy is the energy a charge has because it resides at some electric potential. U is equal to Q naught times V. Any charge placed at a potential will have potential energy. Potential energy is not a vector, but it can be positive or negative. V can be positive or negative. Likewise, a change in potential energy is related to a change in electric potential. So if a charge moves through a potential difference, that's what we mean by delta V, then its potential energy will change. So another example. Let's say we have two big parallel plates. One's positively charged, one is negatively charged. We know there's going to be an electric field between the plates. The electric field lines always point away from positive and towards negative. So our electric field is going to point to the right with the way I've drawn this. Turns out electric field and potential are directly related to each other. What would you expect the equipotential surfaces to look like between these plates?
Vertical lines.
Vertical line. So any charge placed along that vertical line will have the same amount of energy regardless of where it is on the line. There would be multiple vertical lines representing lines of equal potential. So if a charge moves from here to here, it's moving through a potential difference. Now delta V, electric potential is high near positive charges. Electric potential is low near negative charges. If this was my initial point and this was my final point, delta V just means V final minus V initial. If we start here and move to here, so start at initial, move to final, will delta V be positive or negative? Negative. Delta V will be negative because we're going to a lower potential. We're ending up at a lower potential than where we started. Smaller value minus a bigger value gives you a negative value. So with that quiz we just did, where we said that delta V was positive 1800 volts. Well, if you think about it, if I have an electron and I put it in this region, where is it going to go if I let it do what it wants? It's going to head to the left. It will move from a lower potential to a higher potential because it's attracted to the positive plate. But please keep in mind, its change in potential energy was still negative. Its potential energy still decreases. As delta V is positive, the charge on an electron is negative, so delta U is negative. Its potential energy gets smaller and smaller. It gets more and more negative as it moves towards that positive plate. You can see that from this equation. Even though V is getting bigger, since Q naught's negative, we're getting more and more negative, which technically is smaller and smaller. What if I move from the same initial point to some final point down here? So instead of going this way, I go this way. Will the change in energy be any different? No. We're still moving through the same potential. So the potential difference is still the same. It's still negative. So any motion parallel to the field This motion can be broken up into a piece perpendicular to the field and a piece parallel to the field. Any motion parallel to the field results in a potential difference. Any motion perpendicular to the field, there's no change in potential. So the only way we have a delta V is if we're moving along an electric field line. We can move with it or oppose it, it doesn't matter. That will just change the sign of delta V. So something that would be kind of handy would be to have a relationship between delta V and the electric field. The two are related. They're not equal to each other, but they are related. You don't find one without the other. So that will take us back to what we were doing yesterday, where we said delta U was the negative integral of force dotted with displacement. That's just our work equation. Work is the integral of force dotted with displacement. Negative sign comes from the conservation of energy. So delta U is negative integral of force dotted with displacement. But we know delta U is Q naught times delta V. So the change in potential energy is equal to the test charge, whatever charge is going to fill the energy change, times the change in potential it moves through. Force, we know that any charge in an electric field will fill a force, so I'm going to replace force with Q naught times E. Have a Q naught on both sides, so they'll cancel. So delta V is equal to the negative integral of the electric field dotted with the displacement. This is our relationship between delta V and the electric field. It's a dot product equation. That means we get a scalar answer, and it also means that we only multiply the parallel components. So it's only the component of the electric field parallel to the displacement, or the component of the displacement parallel to the electric field, that actually correlates to the change in potential. In this example over here, between two parallel plates, the electric field would be constant. If the electric field's constant, it comes out of the integral sign. Integral of dr is simply some sort of distance. It's still a dot product equation. That hasn't changed. The only difference is if E's constant, we can pull it out of the integral sign. Integral of dr is going to be whatever distance we move through. Please keep in mind this equation, though, is only valid if the electric field is constant. If it's not constant, you do have to integrate. So basically, there is a potential difference between these two plates. Whenever a capacitor, this is basically a capacitor, whenever a capacitor is charged, there's an electric field between the plates, which also corresponds to a potential difference across the plates. So one plate, the positive plate, is higher than the negative plate, which is lower, and there is some set delta V. The electric field for a capacitor, eta over epsilon naught, from last section. The potential difference is going to depend on the distance between these two plates, how far apart they are. So eta over epsilon naught times d, the distance between the plates. Now the negative sign. This negative sign is only applicable if our electric field and our displacement are in the same direction. So this, the way we've drawn this, assumes we started at the positive plate and ended at the negative plate. What if if we had started at the negative plate and moved to the positive plate? It'd be positive.
Passive and active sign convention. That's what we call it in EE.
Is it?
When you go from negative to positive or positive to negative, you're just saying.
Yeah, so the sign is all that changes. Positive, negative versus negative, positive. So a lot of times, actually, when we get to capacitors, which will be very soon, we tend to talk about the absolute value, because really that's what's important.
Is that just a,
This is a big old transformer from a
so it's just a transformer?
big old neon sign.
Yeah, I think we've got that. No, we just, oh yeah.
So transformers, we'll talk a little bit more about them when we talk about magnetic fields. But a transformer basically can either step up voltage or step it down. This one's a step up voltage transformer. So it takes our wall outlet, which on average is 120 volts, and it's going to step it up by a factor of about 1200.
Wow.
All right.
So it takes our voltage and bumps it up really high. Now both ends here, one end, well, the direction's going to change, but there's a potential difference between the two ends of this transformer. So one end is higher than the other. So we have a delta V between the two ends. With these metal hangers connected here, it turns out with any conductor that's connected, once equilibrium has been reached, the electric potential is the same everywhere on that conductor. So whatever electric potential this end of the transformer has, this whole hanger right here is going to have as well. So the potential is going to have a set value along this leg, and likewise this leg is going to have a set voltage as well. Delta V is the same regardless of what two pieces of the hangers we look at. So at any one moment in time, the delta V is the same. The difference is how far I have the hangers apart from each other. The farther apart they are, the weaker the electric field will be between them. If you have a potential difference, you have an electric field. Period, end of story. Okay? So the farther apart these are, the weaker the electric field is going to be. The closer they are, the bigger the electric field is going to be. And then this goes back to what we said when we looked at the Van de Graaff. When the electric field reaches a big enough value, the charges are physically forced to jump and to leave. The force is too big to hold them on the object. So we'll see if we can get this to work. So yeah, basically ionizing the gas in between the two. Notice the jump always starts down where it's narrower, where the electric field is higher. And then just due to, I would imagine, density changes, it rises.
Creating fire out of air.
It would kill me if I touched it. Yeah, the voltage is far too high, and it can draw a significant amount of current, which would significantly alter said organs in your heart.